V, it's the same flow, so V. Then next is we start with the motion of this end, because we are ultimately interested in modeling this stiffness and damper as well. So we have one junction here for V naught, and you can see that it has to track this profile, and the velocity that is imparted on account of this profile is V naught. So it is something which is imposed on this end, and so we place a source of flow, and then we take the relative motion between these two. We have already discussed this in one of our previous lectures, so here is how we assign C and R. So our bond graph part is complete. What is the next logical step? Cause and effect. So first of all, let us number all the bonds so that we can identify each and every bond. Then we place the causal strokes. So we start with the first stroke, that is for the sources. So both the sources have been causal. Then we have, if you continue with this junction, with this causality, for this junction someone has brought in, a bond has brought in the information of flow, so this bond has to obey it, but we are stuck over here. So let's continue from this side. Here we already have got a stroke because of this source. Here we have this I element, and we are going to put a causal stroke here. Then, in order to respect the causality of this one junction, we are going to place the causal stroke here. We place the causal stroke here, and here, and here. Okay. This entire system is now in proper integral causality, and we can identify the states of the system. How many are we going to have? Only two. They are this momentum on account of this mass and the deformation of this spring. Okay, they are indicated here. Next is, we start with our questions. We ask the first question: what do the elements give to the system? Okay, and this we ask for all the elements, and this is what we said as an output question, output. So here E3, what does this source give to this? It gives effort 3, and effort 3 in terms of parameters can be written as Ft. Ft may be provided experimentally, as Professor Bhowmick says, or it could be based on a desired simulated function as you want. Okay, anything, it can be input over here. Next is, what does this source provide to this? It provides flow. So this flow is equal to V naught T. It could depend on the profile. This profile could be measured, or it could be analyzed, or it could be provided by the user. Okay, it has to be provided in the form of an equation or in form of data. That's up to the user. Then F1, what does this element give to this? It gives effort of flow. If you look at the causality, you can see clearly that this I element receives effort, so it gives flow to the system. So flow is given as P1 upon M1. Then the next element here, what does this C element give to this? Effort. So it provides effort, and if it is a linear spring, the constitutive equation is K into Q. Then we have this R element here. Now I have taken this a little lower down deliberately. So what does this provide? It gives an effort, and this effort is R into flow 5. if we assume that it is a linear viscous kind of damper, and flow 5 is equal to, where is this information of flow 5 coming from? If you track the information of flow 5, you can see that it is coming from here, because in this one junction only one bond is bringing in information of flow and it is coming in from here. Okay. So flow 5 is equal to flow 7, and who is bringing in this information of flow 7 into this zero junction? Flow 7 is flow 6 minus flow 8. Okay. So flow 7 is equal to flow 6 minus flow 8. Now what about flow 6 and what about flow 8? What is flow 6? Flow 6 is coming from flow 1. Information is coming from flow 1. And what about flow 8? Information of flow 8 is coming from flow 4. Both flow 1 and flow 4 have been defined here earlier. So flow 1 also is in terms of states and parameters, and flow 4 is also in terms of states and parameters. So you can write this as R into P upon M minus V naught. Okay. Next is, we go to the second question. It's just a 2-question algorithm. It's very simple. Just you start with the output and then with input. That's all. It's an output input based algorithm, and it can be automated. You can see how systematic it is. First is, we ask this question: what does the system give to the elements with integral causality? Because it's only the elements with integral causality which are going to contribute states to the system. So here you have E1 is equal to rate of change of momentum, and this E1 is coming from where? If you see this effort 1 is coming from effort 3 minus effort 6, effort 3 minus effort 6. Now what about effort 6? Where is it coming from? What about effort 3? Where is it coming from? Effort 3 you have already specified earlier. It is Ft. So you don't have to worry about it. But what about effort 6? Effort 6, if you trace the causal path, effort 6 comes from effort 7. So effort 6 comes from effort 7. And effort 7 has already been worked out earlier. No, not yet. Effort 7 has to be worked out. And effort 7 is effort 2 plus effort 5. Okay. So you can see that effort 7 is equal to effort 2 plus effort 5. Effort 2 has been worked out earlier here. Effort 2 has been worked out here. And effort 5 has been worked out here. This is effort 5. Okay. So you can see that the right hand side for this equation is equal to Ft minus K into Q2 minus this term, and now the right hand side is in terms of states and parameters. Okay, so on the left hand side you have the derivative of the momentum, and on the right hand side you have the states and the parameters. They may be linear, non-linear, it doesn't matter. You can handle any system now. Let's ask the same question now to this integral element. What does the system give to this element? Effort or flow? You can see the causal stroke. The causal stroke is away from C, so the C element is receiving flow. So the system is giving flow. That means the input to the C element is flow. So flow 2 in this case is corresponding to the rate of change of its deformation. Okay, Q2 dot. And what is this flow 2? Where is it coming from? It is coming from flow 7. and flow 7 is coming from flow 6 minus flow 8, and you have done all that over here. You see, flow 7, flow 6, all that has been done, so you don't have to worry about it. In fact, flow 2 is equal to flow 7, and flow 7 has been worked out, so it is equal to P1 upon M1 minus V naught. Okay, so now let us see, we have both the equations with us. We have the complete dynamics for this system represented in the form of two first order differential equations. The left hand side indicates the change of the variables, okay, the change of state, the rate at which it is changing, and the right hand indicates the relationship with the states and the parameters. Okay, this particular form is called as the cause effect form or the first order state space form. Okay, you can write it in matrix form, then it becomes a first order matrix state space form, but that form is suitable generally when you are dealing with linear time invariant system analysis. Let's proceed further, and now let's take perhaps we have time for another, should we go to simulations or should we? I think we have 10 minutes, so we can start with the basis for simulation, and once we go through that, then we can straight away step into coding, computer coding, which we will take in detail in our 2 lectures tomorrow. So suppose we have a system like this. We have a set of derivatives, first order derivatives. So you can see that using bond graph, we can derive equations in this form. Can you see it? So we can derive equations in this form. X1 dot is equal to F1 is a function of maybe state 1, state 2 and so on, up to, say, if we have n states, we can have n states, and we can have inputs, say U1, U2, let's say we have m inputs, and let's also say we have explicitly time. The same thing we can do for all the states. We can have n of them. So for n states we have n differential equations like this, Fn, and instead of writing each and every time x1, x2 up to xn, I am going to compact it and write it as x vector. It's a state vector indicating the order in which these states have been taken. So this is a state vector indicating this order. In the same way, we can use the inputs and put them as, instead of writing all of them over here like this, we could represent them in short like this, and time is a scalar which is explicitly shown here. So one can cast this in matrix form. Our state vector therefore is x vector at any time t. It can be taken as x1 at time t, x2 and so on up to xn, and